This is Lab Practical 4, RLC series circuits. Here we can see we've got 180 ohm resistor, we've got a 1 microfarad capacitor, and we've got a 47 millihenry inductor, and powering the circuit we've got a signal generator which is initially set at 300 Hz 5 volt. So we've got our series circuit here. As we know, in a series circuit current flows through all components, however voltage across each component varies, and that is what we're going to look at in this experiment. So we've got the signal generator set up at 5 volt RMS. Just to satisfy ourselves, I'm going to put a voltmeter across the circuit, and we can see here that we've got 4.69, 4.7 volts across the circuit. That's because we're drawing a load from the signal generator which is dropping the voltage because of the internal impedance of the signal generator. So we're going to record the supply voltage throughout the experiment. So we've got our phasor display unit here, we've got our components, we've got our signal generator connected across them. Let's connect the phasor display unit. So we're going to connect channel 1 of the phasor display unit across the resistor, because from previous labs and from theory we know that voltage and current are in phase across the resistor. So we can use that as a reference. That tells us the phase of the current basically. We're going to put channel 2, the yellow channel, across the capacitor. Make sure you keep the polarity the same, so it's red, black, red, black. Across there. And we're going to set the blue channel initially across the inductor. Again, red goes first and black goes second. So we have our circuit set up. So we have red across the resistor, yellow across the capacitor, and blue across the inductor. So if we look at our phasor display unit, initially it's showing the biggest volt drop across the capacitor. That's because the capacitor has a high reactance and is the biggest current limited component in the circuit at the moment at this frequency. We can see that the phasor display has two sets of units. It has the voltage in polar form there, so that says 5.2 volts at minus 90 degrees, and we also have it in rectangular format, so we have 0.03 minus J 5.2 volts. What that basically means is this is volt drop due to resistance in the circuit, this is volt drop due to reactance in the circuit. Now if we look at the inductive reactance, why is that not 90 degrees in front of the current? And the reason is that inductors are made of copper, of coils of wire. Those coils of wire have resistance, so in real life an inductance can never lead the current by 90 degrees because we have always a resistive element. And here we can see we've got 0.39 volts drop due to the resistance of the inductor, and we've got 0.995 volt drop due to the reactance of the inductor. So during this experiment, the volt drop across the inductor, we're going to take the rectangular coordinates, we're going to take the rectangular value of the volt drop, so we can measure the volt drop according to resistance, the volt drop according to reactance, and for all of the components we'll take the polar form of volt drop. Okay, so we'll measure our circuit. So this is at 300 Hertz. We'll take our measurements, but we need the measurement for the supply voltage as well. So we're going to move channel 3 and put it across the supply. Now we can take this reading as the polar form. So we'd take this volt drop here, and we can see that the voltage across the supply is lagging the current by 62 degrees. So this circuit is basically a capacitive circuit at this moment in time. So we'll put those back, and we'll increase the frequency to 400 Hertz, and we can see that the volt drop across the inductor has increased and the volt drop across the capacitor has decreased. Again, we'll look at the voltage across the circuit, and we can see that we're still lagging the current, lagging it now by 49 degrees. So this is still a capacitive circuit. So we'll take those readings, enter them in your lab notes. We'll return that channel 3 across the inductor, and we'll increase the frequency again to 500 Hertz. So at 500 Hertz we can see that the voltage across the inductor has increased, the volt drop has increased. As the frequency gets higher, an inductor tends towards an open circuit, and the volt drop across the capacitor has decreased because as frequency increases, a capacitor tends towards short circuit. So we'll take those readings and we'll move channel 3 again across the supply. We'll notice that we're getting nearer to the current. So we're minus 33, we're lagging the current by now. So we're still, overall, we're a capacitive circuit. So we take those readings and we return channel 3 to across the inductor. And we'll increase the frequency to 600 Hertz. So again, we see the volt drop across the inductor increasing. The volt drop across the capacitor is decreasing. And we'll take our readings and then we'll move channel 3 across the supply. And now we can see that we're still lagging the current, so it's still a capacitive circuit. The overall, the biggest current limiter in the circuit is the capacitive reactance, but now we're only lagging the current by 16 degrees. So let's put that back into channel 3 across the inductor, and we'll increase the frequency again to 700 Hertz. So we're at 700 Hertz, and we can see that the volt drop across the inductor has increased, the volt drop across the capacitor has decreased, and if we look at the reactance, the volt drop due to reactance across both components, we can see that we've got minus 3.94 volts there, and we've got plus 3.914 volts there. They're essentially the same, the reactance is the same. However, they're 180 degrees apart, so they're going to cancel each other out. So if we look at the voltage across the supply, we can see that the voltage and the current are now in phase. The only thing that's drawing current in that circuit at the moment is the resistance, purely because the reactance and the inductive reactance are cancelling each other out. So that is what we mean by resonance. That's when the reactive components have cancelled each other out, and the only thing left limiting current is the resistance of the circuit. Okay, so we'll take those readings and we'll plough on. We'll go up to 800 Hertz. So at 800 Hertz we can see that now the inductive volt drop is the highest volt drop in the circuit. So the inductive reactance is the biggest thing in the circuit now that's limiting current. And if we take channel 3 and put it across the supply voltage, we can see that now the supply voltage is leading the current by 14 degrees. So we've now got an inductive circuit. We're now looking at a circuit that is overall inductive. So put that back and we'll increase the frequency to 900 Hertz. And now we can see, as we expect now, the volt drop across the inductor has increased, the volt drop across the capacitor has decreased, and the circuit is becoming more inductive. So we've got now the voltage is leading the current by 26 degrees. So that's all your readings taken. So what you need to do is enter those readings into your lab book and calculate the impedance, the current that's drawn in the circuit, the inductive reactance and the capacitive reactance at each frequency, and draw the graphs that you're asked to draw and fill in your interpretation of what is going on in this circuit. Okay, thank you very much. Good luck.